So what's up?
So, just to check my understanding, Ka is a measure of basically how well a molecule gets divorced, like how well it disassociates into its components.
That is not a way I would have referred to it, but yes, that's exactly it.
I heard somebody say that the pKa is how tight an acid holds on to its proton,
Well,
but
go ahead. Go ahead.
that definition didn't really make sense to me.
Well, okay. In the same way that Ka is a measure of how well it keeps that proton, because that's exactly what it measures. pKa measures it in the same type of way. The only difference between those two is that one is the negative log of the other. So it's very similar to how we talk about H plus concentration versus the pH. It's the exact same relationship there. So
Okay.
we're looking at bigger numbers when we talk about Ka, and the pKa is just a smaller number that's easier for us to manage.
Okay, so it's the same thing.
Yes.
Okay. Um, for our calculation of um hydronium,
Yes.
that's the POH, right?
Now the hydronium is the H plus, the H3O plus. That's what that refers to. Oh wait, hydronium? Wait. Okay, now I'm questioning myself, so let me ask. Yeah, H3O plus. Sorry, my brain just wasn't sure.
It's early in the morning, I get it. Okay. For I understand the first ice table that we did with an acetic acid dissolution
Okay.
and a Ka calculation.
Yes.
When we have the buffered solution, you mentioned that there's extra information we have to include, which makes sense to me.
Yes.
But I don't know how to factor in the buffered solution even to the reaction equation.
Yes. Okay. So what I am about to show you is how we do that. And we're dealing with acetic acid. There are many different ways that I can write this. One of the ones that I can use. Oh yeah, I need to share my screen. So one of the things that I can use is C2H3O2H. That's one of the ways that we write this. When that dissociates, we get the C2H3O2 minus plus the H plus. This is the reaction that we use when we talk about Ka. So this is the only equilibrium that I want to talk about or need to consider.
Okay.
Now, what happens is that when I set up my ice table, I know that this is going to be the way that we're considering it. The negative X goes under the acetic acid, the positive X goes under the acetate ion, and the positive X goes with the H plus. The problem is this right here, because I already have some of that from the buffer solution. So initially, I have a 0.20 molar here for the acid, but I also have a 0.20 molar for the acetate ion from the sodium acetate. And then this H plus is what we're trying to look for. The presence of this ion means that this reaction is not as capable of going forward because I already have product. And so this shifts this reaction backwards. So the overall reaction from Le Chatelier's principle goes that direction. And so we end up with a lower pH because of that. There's less dissociation of the acid because of the presence of the anion. It's called the common ion effect. And
Okay,
so do our
would the
Go ahead.
equilibrium for acetic acid still be the same molarity?
Well, this is what I started with. So I've only done the ice part. And as far as the K goes, that's still going to be the C2H3O2 minus. And of course, it is a Ka since it is an acid. And H plus over the C2H3O2H. We just end up with these two no longer being equal because there's already this species present. So when I plug into that K, I end up with 0.20 molar here. This is my X, and then 0.20 molar there. We're talking about the experiment, so we just had some questions about the experiment.
Are we doing lab? Like, how are we going to be doing lab?
I sent you all the data, so it's a virtual lab. So you got data, you'll have to analyze that just as if you'd been in the lab, but you won't have to physically collect it.
Okay, and we'll still do the same process in our notebooks and everything?
That's the idea, yes.
Okay.
But yeah, I sent you the spreadsheet that has all the data in it. And it's a ton of data, so you don't have to hand write all of that. You can just say all of the data is in the Excel. That's perfectly fine.
Oh, like for
Okay.
when we put data, when we say data in our notebooks?
Yeah.
Okay.
So when you get to that part, you say, this is what was recorded. I measured pH versus the amount of either HCl or NaOH that was added. And all of that data can be found in the Excel table. Okay, you had a question.
Me again? Oh, how many sig figs should our acetic acid molarity be?
Well, let me check the information from the lab notebook because I actually don't remember what's in the lab notebook. So let me check. Because I'm pretty sure that what was written on the bottle was something like 0.1998. So in that case, we'd want 4 digits on the acid, if that's what was recorded on the bottle. I think the lab manual states that it's 2. And so I took it out of here. Oh, not that one.
This is for experiment 2, correct?
We are talking about experiment 2, yes.
The one we just did. Alright.
Yes.
Hope everyone's staying safe. Everyone's prepared.
I'm good.
Yeah, we cleaned up yesterday when I got back from class.
So if I finally get to the lab manual, which I'm opening over here on this other window. Ta-da. So what the lab lists is 2 sig figs, but I think that I think the bottle that we had was listed as 4, and that's because it was actually measured that way.
I'm talking about the equilibrium calculation for acetic acid.
Yep.
Like the number that I got from subtracting 0.20 minus 0.0021. There are 4 4 digits in the math,
Yep.
but I feel like there should only be 2.
Well, okay. When we report the final answer based on the 0.20, that would be 2 sig figs. That is correct.
Okay.
And since we're maybe waiting on other people, maybe not. If you want to continue talking about the lab and you have other questions, that's fine. Let's talk about it.
So for the Alex stuff, the Alex is making me do some like introduction, like problems. Is that supposed to happen?
In terms of when you first go into Alex?
Yeah, like I guess I've never used it before, so it's making me like do a bunch of different things, and then I guess I can access the assignments.
So you should be able to skip that if you choose to. Because I've always had an option to skip it. In my new classes, it treats me like I'm a new student. So if there's always a skip tutorial, skip tools bit. So that's what I've always done. But if you need the help, then feel free to do it. But yes, the assignments are after that. And if we
I was gonna say I've yet to do the assignments because I can't get the. I was trying to. Where in the world?
so there is a knowledge check. Okay.
Yeah, that.
Well, the knowledge check should have nothing in it. And there's right here, skip knowledge check.
What? Where?
Down at the bottom. Right there.
Oh, hold on.
Now, I will tell you that you can completely ignore this, and there's a reason for that. We are not using Alex in the adaptive format, so your level of knowledge of the course is not required. So you should see this. If you
Yeah.
don't see that,
I didn't.
then you may just need to put in all the like X's answers of some sort for everything, and then you should be fine.
Okay. Yeah, because I don't see that. So
So that's one of these cases where and it's going to complain, and that's fine. And I submit it again, and it goes past it. I mean, it'll complain, and that's perfectly fine. Because again, we are not using it in that format, so it doesn't matter what your current level of knowledge is. The only reason you might want to look at that is because you may have gaps that you need to look at what these things are from 110 that maybe you didn't understand that well. That's the only reason that it's there.
yeah.
And unfortunately, I can't skip it. So, but just choosing anything is perfectly okay. And again, it may complain, but that's all right. That doesn't matter.
Going back to the ice table,
Yes.
I thought that we needed at least one value at equilibrium in order to do this like X math for the equilibrium. I understand to get the Ka that we can use X.
Well,
But since we found X, is that what we plug in for all the X's?
so anytime it says X, that value has to be the same. So if this equilibrium was such that there was a 2 out in front of this, then this would be a 2x. Because that's how that goes. We match the stoichiometry from the equation, which is why we write the equation at the top, to the x's that we write in the change row. So if you've got an x, it's always the same value. So when we find this one right here, which is 10 to the negative pH, that gives me my H plus. That is the same as what we would be looking for without the contribution from the 0.20. So this would be the same value as this. But our equilibrium value here would be 0.20 plus that x. And we normally ignore that x. And this is 0.20 minus x. And we usually ignore
I
that.
understand that, but I don't understand how we find the value of X.
So we have a pH for that solution. So we take 10 to the negative pH. That's equal to the H plus concentration.
That makes so much. Very much. Appreciate your patience.
Oh, I totally missed that.
Calvin, we are talking a little bit about the lab that we did, so bear with me a few minutes. We'll talk about this and then we'll get to the lecture part. I'm just seeing if anybody else is going to show up.
Yes, please. This could actually help out. I was trying to do my lab last night and didn't get too far.
Okay. Well, do you have any specific questions you want to talk about?
I'll be perfectly honest with you. I was really tired at work. I tried to look at it, and I just couldn't look at it with a fresh brain.
Unfortunately, I understand that, and I'm sorry that was the situation you were in.
So, Dr. Hartley, is this the rice table that's on question 3, I believe, on the...
This would be the one for question 3. That's correct.
Okay. And where did you get the what's the starting point on this? Oh, was the 0.20 molar? Is that the
So
starting point?
Yeah, this is our buffer solution. So our initial conditions are the 0.2 for the acetic acid
Okay.
and 0.2 for the acetate ion. And actually the 2 doesn't belong there. I was just demonstrating something with that.
Okay, and I calculated the sodium acetate to be 0.196 moles. The molarity.
Yeah, it's close to 0.2 because I'm just using the value out of the lab manual, but I'm sure yours is a little bit different than that. So that is what you would put in for the acetate right here.
Okay. I gotcha. Thank you.
Sure.
So for this calculation for the H plus concentration,
Yep.
I got around 2.14 times 10 to the negative 5.
So what was your pH?
4.67.
So I take 10x to the negative 4.67 and I get 2.14 times 10 to the negative fifth. Yep.
That's not a molarity though.
That is a molarity. because we've gone from 10 to the negative pH to back to a concentration for H plus, and so that has to be a molarity. Chewy.
And those molarities are really, really different because pH is a logarithmic scale. It doesn't mean that I did something wrong.
Well, the other thing is that in a situation where we have a large excess, and that's what this is, of the acid and this buffer, I would expect the H plus to be small because that reaction is so far driven to the left. Because Le Chatelier says that this is going to go backwards, that means that that H plus has to be small. The very presence of this means that any H plus that's generated immediately combines with one of those acetate ions and goes back. We only have a very small amount that because of the equilibrium can exist.
Professor, what should get 10 to the negative pH in the equilibrium for the H plus?
So I'm looking for the H plus concentration, and that's equal to 10 to the negative pH. That's one of the things out of the fun box. So that's where that comes from.
Okay.
It's how we take the anti-log of the pH. And of course, it's negative because it's a negative log. So is it okay if we come back to this after the lecture?
Yes, yes.
Okay. Then I'm going to go ahead and get started with that. Now, just a couple of comments for people. You probably saw what I posted on D2L. I have taken out of these lecture slides some of the working through things problems. I'm going to record walkthroughs on that for anybody who wants it. Okay, so those slides are still available to you. The ones that have less stuff in them, I am posting separately. So this version of this deck has slightly fewer slides. And I've added a couple of things to this one to talk about the two experiments that we've been working on, because I was grading experiment 1 yesterday, and I know we had some issues with experiment 2, so I want to talk about those two things. As far as the end of the previous lecture, so the end of lecture 2, I will post those walkthroughs as well, because that's all we had left in that lecture was questions on how do we do this, how do we do that kind of thing. So I will post those recordings as well, and if anybody has any issues with that, that's fine. We can talk about it. Okay, so just so you know, I don't want us to get too far behind, but I need to make sure that everybody's got what they need. Okay. So what we're going to be talking about today is Ka and Kb. Those are the two things we'll be talking about. So acid ionization constants, base ionization constants. We'll talk about the relationship between the ionization constants for acids and their conjugate bases. And then we'll talk a little bit about the buffer solutions. And there's some information in here about the experiment too for the buffers, so we'll talk about that as well. Okay. So let's talk about a little bit about experiments 1 and 2. So I just wanted to walk through some of the stuff, and this is from the lab that you already turned in. So I just want to walk through some of the stuff that I saw so that we can talk about what was there. Now, your initial data for the ICE table that you were asked to do for this calculation comes from these calculations that you did about the concentrations of Fe and SEN in these initial solutions. So these numbers right here should match what you have in that ICE table. Okay, we have nothing initially for the FeSEN. Okay, so there's nothing there. And of course, if we look at our X values, we know that for every FeSEN that I make, I need an Fe and I need an SEN. So those two are going to be negative X, and then we'll get a plus X for the FeSEN2. Now, what I'm actually looking for is all of the values that go into E so that I can calculate a K. So I know that my K expression for this is equal to the FeSCN2 plus over the Fe3 plus times the SCN minus. And so I need all three values to be able to calculate that K. One of these values comes directly from our calibration. So I know that this particular solution, this first one I'm talking about here, has a 57.42% transmittance. Now this is data that I have from previous. It's not going to match exactly what you guys have because the two groups had different values. So it's not going to match exactly. That is then converted into absorbance, and then that gives us a concentration for the FeSCN. Okay, so that is that number right there, and that's where that comes from. Is I took this right here and I put that right there. Okay, now I also know that my expressions right here are going to be what I started with, that 3.33 times 10 to the minus fourth minus that X value. Okay, and that's for both of those. And so that's how I got the numbers that I plugged in here. Okay. Once I plug all of that in, I end up with 379 on my calculator, 3 sig figs. Okay, it's a little bit different than what was calculated here, but that's because Excel holds all of those decimal places, and my calculator can't hold that many, so it's a small rounding error. That's the kind of thing we're talking about for rounding error. So I get this calculation. I know that I get this for all of these. This is how all of them are calculated. And then I can do the comparison between them to see how, are they good? Are they bad? Are they okay? What we see on the first one, this very first one, which is the lowest concentration of either ion or SCN minus, is that that value is a little bit high. And the reason that value is a little bit high is because it's very difficult for the spectrophotometer to ignore the background room light at that concentration. So that's why we get that value. It's artificially high for this right here. Okay, so that is the why it looks like that. Okay, so I just wanted to make sure that you guys know that our ICE tables, my main point in talking about this is that our ICE tables can be used in any number of ways. Okay, we can use it to find an equilibrium concentration. We can use it to find an initial concentration. We can use it to find all sorts of relationships. But that's all based on us putting in what we know at that time. So if I know information about the equilibrium and I know what the balanced equation is, then I can figure out what it was initially. Okay, so that's how this works. The other thing that we need to talk about, and this is based on the post lab. So if everybody's okay with this slide, I'm going to go ahead and talk about the post lab. The post lab is a little bit different. So our stoichiometry in our post lab is different than it was initially. And so we're trying to extend this idea of what we were talking about. I know that we start with SO2 plus O2 goes to SO3, and this should be a 2 out in front of here because that's how we balanced it. That was the first part that you had to do. Then you had to write the K, which is the SO3 squared over the SO2 squared times the O2, and that's equal to 17.1. Then I set up my ICE table based on that equation. Okay. Now, with that, I end up with the 2 out here, the 1 out here, and the 2 out here. And so when I get to my change row, that row has to reflect that stoichiometry. So I need to have minus 2x here, minus x here, and plus 2x here. Okay, so those are the things that would go into that K expression as it's written. And remember, when we do that, we write our K, and that's equal to the SO3 squared, we have 2x that we put in for that, and that's squared. On the S of 2, we have 2x here, and that is squared. And then we have our x. So that, if we were solving based on having absolutely no values, that's what we would have. Okay? So whatever that change is, whatever appears there, that's what I have to plug in when I start to solve for things. Okay. Remember that when we do that, we have to do whatever we did to the x. So if I'm trying to square this concentration, I have to square the 2 as well. So we end up with 4x squared over 4x squared times x. Okay. So we have to remember that whatever that change row is, that goes in directly for that concentration if we're solving. And we have to treat that in the same way. So if I've got that 2 out there and I have to square that, then that becomes a 4. If I have a 3 out there and I have to cube that, that becomes a 27. So make sure that that gets carried with it, because if it doesn't get carried with it, then your math gets messed up. Okay? So that's how that works. And that was why I wanted to talk about that part of it. So when we put in actually plug in our values, we just plug in the 0.126 that we were given in the problem, that's squared on the bottom, and our 0.0582 here, and then we're solving for this concentration of the SO2. That's what we're solving for. And so we do a bunch of happy math, and I end up with 0.126, which is the value that I put here in green after I do all the happy math. And then the next question asks me, what's that initial concentration? Well, I know that this value in green is 2x. I know that this value right here is x. So I can take this thing right here, my equilibrium, add the 2x to it, and that gives me my initial concentration. And so that's how we end up with the 0.251. Okay? So that's what we're looking at there.
Professor, I actually have a question on this.
Yes.
I think this is where I got stuck on, because if you take a look at the change, right?
Yes.
On the ice table.
Yes.
On the reactant side, you have negative 2x and a negative x. And on the product side, you only have plus 2x. I thought it was supposed to be equate to 0.
No. Okay. Your stoichiometry is where we determine mass balance. We do not determine it using these x's, because the x's don't always work that way. We're only using that as a variable because we need to find these things, but they don't come together as a 0. They don't.
Okay. Makes sense now. Thank you.
Sorry. Yeah. So we've got with that. So remember that you need to make sure that you've got the correct balanced equation. This is yet another place where we need to make sure that we've got that thing balanced. And even if you're handed an equation, make sure it's balanced, because it may not be. And that may not be intentional. That may have been a typo. It could have been an error. It could have been, I mean, there are errors in the lab manual. I've seen him misbalance things. So there are things that we have to check for and make sure that it's actually working. Because if we try and do math in an ICE table with an incorrectly balanced equation, it will not come out correctly. So there's that part of that. So again, we need to get comfortable with working with our ICE tables, and we need to be able to do that from pretty much any point. We need to be able to either start at the beginning with our initial concentrations and work down, or we may be given one of these X values as an equilibrium, and then we have to go to, okay, if I know what this one is, then I should know what this one is. Or I may be asked, what is, something that I started with? That's the kind of thing that we're looking at. Now, I want to talk a little bit about what happened in the next experiment. So when we did experiment 2 in the lab, and Kelvin, you should be glad that you weren't there because we were having equipment issues. I know that the data that you guys got is crazy. I'm absolutely aware of that. All of you were in a place where you said to me, this is nuts. Why does it look like this? That's good, because you knew that it was nuts. So something inside you said, wait, this is not what it's supposed to be. That's important. Okay. And it's a good place for us to say, okay, what do we do in that situation when this happens in the lab? One of the things that we may get asked to do, which is what I asked you to do, was to push through and see if that data looked correct from the trend perspective. which it did for one group, but not the other. Okay. So in that case, when we had our, our acids that we were adding to water, the pH went down. When we had our base we added to water, the pH went up. That was at least the right direction. Okay. The other group did not have that. So then we went, okay, I'm not going to make you work with that data because that trend is not working. Okay. So that's important. We don't always have equipment that works. Unfortunately, the equipment gets dealt with by lots of people and it doesn't always get stored the way it's supposed to. And pH meters are really, really sensitive. So it may be that they need some help. But it takes 3 or 4 days to recondition a pH probe. So we didn't have time for that. We just didn't. So that is something that we have to be aware of. For you guys, what's important is that you know that it was messed up. And you can talk about the fact that it was messed up. And how did you know that it was messed up? Okay, it's not your fault that it was messed up. For the group that was given data, this is the set of data that they were given. Now, I apologize because this data was not supposed to end up somewhere where you could see it, but I put it in 2 different places and didn't recognize that I needed to change it in one of them. I'm trying to stop doing that so that this doesn't happen. But you can see what the data was supposed to look like. And I show this to you because we need to talk about what was supposed to happen in this experiment. So when I'm looking at a water solution and I add HCl to it, my pH goes down by 2 pH units. That's a huge change. When I add the NaOH to that, the pH goes up by about 3 units. That's a huge change. When I'm looking at my acetic acid situation and I add acid to that, that's not a huge change, but it is a change. We add more acid to it, and so we get more H+ that we measure. We have to look at the equation for this when we talk about what happens with that. Sorry, I accidentally went to the next slide. Oh, no, that's the right one. Okay. So when we talk about what happens in this process, we're talking about the dissociation of the C2H3O2H to give me that acetate ion, the C2H3O2- plus the H+. So if I add additional HCl to this, I add another source of H+. That's a common ion effect. When that happens, this equilibrium goes backward. And that's why it takes a minute for you to get a stable pH, because that equilibrium is shifting back to equilibrium. We perturbed it, now it needs to shift back. When it does so, the amount of H that's present is higher because of the HCl, but the contribution from the acetic acid is actually smaller. So if we were able to measure the acetate ion, then there would be less of that present because of the presence of the HCl. In the case of the NaOH, that's a slightly different thing. What happens is that this H+ reacts with that NaOH. And so that goes away to give us H2O. And so we've removed that H+. And that removal drives this reaction forward. Okay? So we end up with more acid being put into solution because of that. And that's why we see less of an effect when the NaOH is there, because comparative to water, because it's reacting with the acid. Okay. So that is some of what we're seeing there. We need to be able to think about that in terms of how did we change the equilibrium that was present, and then how did it respond because of that. This is the Le Chatelier's principle, and that's what we're talking about here. Now, when we talk about this reaction, and I'm just going to rewrite it so that we can talk about the buffer. When I have this in here, now I have both this species and this species present. And so when I add things to it, we have to think about how does that affect what I'm seeing. So again, if I add more HCl to this, I'm adding more H+. So I'm adding this here, that's going to drive this reaction backwards more than it did before. Okay, and that's because I have both species present. So it's able to go backwards more because of the presence of both ions. And it has to get back to equilibrium. Okay, when I add the NaOH to this, it does the same thing that it did before. We still are taking and removing this H+. So since I'm removing that H+, I'm going to move forward, but I can do it less than I could do before because of the presence of the acetate ion. So if I have a lot of that acetate ion around, it's capable of reacting with the H plus that's present. Okay. And it wants to go backwards. So it's very easy for it to do that. We can't, because it's already present, it's harder for us to push this forward. Okay. So that's what we're talking about in terms of Le Chatelier's principle. So questions about what's actually going on there and how we talk about it in terms of the equilibrium. Okay. So let's talk a little bit about weak acids. Weak acids are so much fun. So they are the most common acid that we see. These do not completely dissociate. We talk about them in the general sense as HA. The reason we say HA is because it's always a proton with some anion on it. And we usually don't care what the anion was. So we just call it an A minus. Because I know it's an anion, so I call it an A. And it's a negative charge because it's an anion, so we call it A minus. We can then talk about its Ka being defined as H plus times A minus over HA, or this is the concentration of the acid itself, and this is the concentration of the ion. And when we talk about Ka, it is still a K. It is a K. The only reason we call it a Ka is because it's for an acid dissociation. It is not required that you guys remember what an acid dissociation that an acid dissociation is a Ka. But you will see that, and sometimes I will write it, sometimes I won't. I often try not to because I want to emphasize the fact that it's an equilibrium constant. So you'll see me do both. We also have a whole bunch of other Ks that we can talk about. There's a Ka, there's a Kb for base. We'll talk about that a little bit later. There's Kw, which we talked about for the autoionization of water. There's a Kc, which is for concentrations for equilibriums. There's a Kp, which is for pressures in gases. They're not exactly the same, but we can calculate values from one to the other in that if we choose to. There's an equation that we can use to do it. I'm not going to ask you about it, so we don't need to talk about it that much. But I do go through it in some of the slides if you're curious, and I'm happy to talk about it. Okay. Those are the big ones that we've gotten to so far. There are going to be some other ones that we come across this term, one of the big ones being KSP, which is called the solubility product constant. And we'll get to that when we talk about the precipitation reactions. Okay. The whole reason for putting these little, subscripts on them is to indicate what it is that we're talking about. Acid, base, water, concentration, pressure, solubility product. They're all the same thing. And that's why I talk about them in terms of K. Okay. Now, we have to remember that the value of pH is related to the value of K. So the more that reaction favors making H3O plus, the lower the pH is going to be, and therefore the higher the pOH. Larger K values are stronger acids. Okay, so there is a correlation between the value of that K and how much H plus I get. All right. When we talk about this, in order for that proton to come off of that anion, we need to have a weak bond between the H and the A. Okay. That A minus needs to be extremely stable when it has that negative charge. And the HA bond must be polar. And the more polar, the better to an extent. Okay. So if the electrons spend a lot more time on the A, then it's really easy to yank that proton off. It's very happy that way. But HF is one of the really, really great polar bonds. HF is an extremely polar bond. The problem is the size of these guys. So even though my electron density lies like this, the size of those guys is really, really small. And so it's really hard to pull them apart. That's why HF is a weak acid, not a strong acid. So that's the reasoning there. Okay. HF is one of the most common acids for us to talk about in terms of weak acids because it is the easiest one for us to write and the easiest one for us to conceptualize. I also think it's an extremely cool acid because it will eat your bones. I think that's fun. Okay, note for the test. If an acid or base is listed in the strong acids / bases list on page 7 of the exam handouts, and I don't think it's page 7 anymore, I need to change that number, but there is a page that has that strong acid, strong base list, then it's strong. If it's not listed in there, then it's weak. Now, there are tables later in the exam handouts, and again, I need to fix that page, for the weak acids, the weak bases, the diprotic acids, and the triprotic acids. And if you need a value for the K for those weak acids / bases, they may be there or they may not. They may be on the test itself. So look in both places. If you're not seeing it and you think you need it, since this is an in-person class, ask me, because it could be a mistake. I try very hard to write my tests with the exam handouts in front of me so that I know exactly what you're going to have. And I will refer to things that are on those exam handouts because of that. But sometimes I screw up and I think, oh, I'll put it in later, and then I forget to do it. So that may be the case. And for those who are going to the testing center, I will make sure that those values are over there, or that they know how to get a hold of me so that they can get them if that's necessary. Okay? Because I've had them text me during tests before. It's not a big deal. All right?
Basically, if it's not on like the first page where we see the acids and bases, then it's going to be weak.
That's correct.
Okay.
Yes, you can make that assumption. All right. So questions about that?
Yeah. I had chemistry 1 with Alvin. Wasn't there a list of all the strong acids? Like, I understand for the test we don't have to memorize them.
So it should be, if I'm not mistaken, HCl, HBr, HI, HNO3, and then
So 4,
yeah, H2SO4.
then
It
HCl,
says
O3, and
CSI on
HCl.
it and BC.
Yes.
Okay, thank you.
And those should be the ones that are in that list. So questions about that? One other thing I'll tell you is if you go to look for a K for something and you can't find one, it's because it's actually defined as a strong acid. So if you can Google it and there is no response, then that's because it's a strong acid. That's not the situation that we're going to set you up with here. Now, yay, we see rice tables again. And of course we do, because we have acid equilibrium. We're going to be talking about what are those concentrations? How does that fit in with our K values? So let's talk about HF. HF, when it dissociates, becomes H plus and F minus. Okay. Our Ka for that is then H plus times F minus over HF. And that value is 7.1 times 10 to the minus 4. Okay. My Ka, if I have no other source of these things, is then going to be X times X over the concentration of HF. Because we make the approximation that that X is really small comparative to the initial concentration. So even though I know that in this equilibrium row, this should be a 0.5 minus X, we always make the small x approximation and ignore that part. Okay, if you want to go through the big, huge math, this is what it looks like over here. Okay, so you can do it, and that's perfectly fine if you choose to do that. Okay, but what we find is that almost all of the time that X is less than 5% of that initial concentration, and so it's a valid assumption to ignore. Okay. That's the definition by which we can use that. Okay, so if we assume that X is small, then I can say that I have my X and my X over 0.5, which is that initial concentration of HF that you were given. That's equal to the K value of 7.1 times 10 to the minus 4th. That means that X squared is equal to 7.1 times 10 to the minus 4th times the 0.5. And that gives me an X value of 0.019. Okay. If I wanted to know what the pH was, I could take the negative log of that, and that will give me the pH for that solution. That's a very common question for us to ask is, what is the pH of this weak acid, given that it's this strength? Because that's something we deal with in the lab all the time is, okay, if I'm using this weak acid, what is the pH that I'm going to get out of this solution when I make it? It's an important piece of information to have. Okay. And so again, we're setting up the same kind of ice table. We have our reaction at the top. We need to make sure that our X's match that stoichiometry. We put on our initial conditions, and then we solve for that X. Questions about that? And again, I'm showing you the math just for anybody who's curious, but it is not required. Okay.
For
Yes.
this, if x is really small, it won't look like there's much of a change in the difference between initial and equilibrium. Like, in fact, if it looks like if the change is like multiple, okay, so like if our x is like 1 to the negative 4th power,
Yep.
with sig figs, it won't look like the equilibrium is different at all from the initial, will it?
That's correct, and that's why we ignore it.
Okay. Okay, that makes total sense, and that's something that, like, I just wanted to make sure that my lab sig figs were right. I was like, this
No.
looks...
You're absolutely fine. And again, I have students who choose to do it with the assumption and students who choose to do it without the assumption. I don't care how you do it. If you're going to be going on, which I believe that you are, then eventually you will have to do it where you consider it. We don't have to do it yet.
Okay, that makes sense. Thank you.
Sure.
So how do we know if x is going to be less than the 5% of the number value?
You don't have to know. I am telling you that we are going to make the assumption that it is.
So so you're not requiring the quadratic.
No, not at all.
We're always going to be using the small x.
That's correct. I only present it because some people want to know, and they get very upset with me if I don't put it in there. So that's why it's there, but it is absolutely not required. We used to teach it, but we lost people when we were doing it. So, the math gets in the way of the understanding of the material. So I don't want that to happen.
Okay.
Okay. All right. So let's talk about setting up, and I'm going to set up these two just because ice tables are so incredibly important for this first test, and actually everything we do after that. So let's talk about acetic acid. CH3COOH has a Ka of 1.8 times 10 to the minus fifth. What's the pH of a solution of acetic acid that is 5.46 times 10 to the minus fourth molar? Okay. Fairly typical setup for one of these questions. I start with my acid, because for me, I have to have that equation first. I know that dissociates to give me these. So that H plus and the anion, all the rest of the stuff that's left. I can then set this up ICE. Since this is a weak acid, it has one proton on it that it dissociates. This is going to be a minus X. This will be a plus X. This will be a plus X. And I want to know what I'm looking for is this value right here. That's what I'm trying to solve for. The only other thing, two things that I've been told, I have a Ka value. I'm not going to deal with that quite yet. I need to put in this concentration, the initial concentration, 5.46 times 10 to the minus fourth. So I've now dealt with the fact that I'm dealing with that acid. I've dealt with that concentration right there. The last thing that they tell me is that Ka, which I know has the form H plus times CH3COO minus over CH3COOH. That is equal to 1.8 times 10 to the minus fifth. Okay? So that's what I've got there. Now, we always make the assumption that this comes down and we ignore the x. I always write it because it would be wrong if I didn't, but I ignore it because that reminds me that I'm ignoring that value. Okay? So that means that I have a value that I can plug in for the CH3COOH. I am then going to be looking for x for both of these components because I don't have concentrations for either of them. So that gives me my x squared over my initial concentration, 5.46 times 10 to the minus fourth, which is what you saw in the lab. It said x squared over the initial concentration. So that's what I've got here. And that's equal to that 1.8 times 10 to the minus fifth. Okay. So I can do some math, and I can see that x squared is equal to 5.46 times 10 to the minus 4th times 1.8 times 10 to the minus 5th. And that gives me 9.8. And I'm going to carry all of the decimals until the end. Times 10 to the minus 9th. And then if I take the square root of that, my x value is equal to 9.91. And yes, 3 sig figs, because that's what I started with right there, times 10 to the minus 5th. And I get people who say, oh, well, okay, I have a concentration, so I'm done now. Except not. Because the question actually asked, what's the pH? So I have to do something with that number. So even though I found that value, and that value goes right to here, 9.91 times 10 to the minus 5th, and I write it in one place because it's both of those, and my handwriting is too big for me to write it twice, I have to take the negative log of that value to get my pH. And if I do that, I find that my pH equals 4.003. And again, 3 decimal places because I had 3 sig figs. So 4.003 is the answer I would report. Okay.
And that's from the negative log of 9.91 times 10 to the negative 5, right?
Correct.
Okay.
Wait, isn't it an acid though?
Yeah.
So wouldn't that be the POH?
No. No. We solve for H plus. So that is the pH. The negative log of the H plus concentration is always pH.
Oh yeah. Okay, I see.
Yes. So this number is the negative log of that number. Other questions about that one? I'm going to do one more. We're going to do another setup for acetylsilic aspirin, because I can't say that. So C9H8O6 is that acid. It dissociates, gives me an H plus C9H7O6 minus. So all I did was yank one of the protons out of there. So it ends up being negative, and my formula has one less H. Okay. I know I'm going to need a rice table, and I almost always assume that I do for this test because everything is about the rice tables. What is the pH of a solution of acetylsilic acid, that aspirin, that is 6.38 times 10 to the minus 5th. So 6.38 times 10 to the minus 5th. Again, looking at my stoichiometry, I know that I need to break down one of these aspirins to get my H plus and my anion. I'm assuming that those are 0 to start with, because that's the equilibrium that I want to look at. I am looking to find H plus so that I can then take the negative log of that to get pH. The other thing that I know is that Ka for this is 3.0 times 10 to the minus 4th. That's the value that they gave me right here. So I've used the fact that I'm using that acid. I've used the fact that I have that concentration to start with, and I've now used that Ka value. So that takes care of all the numbers that I had. I've made sure I've accounted for those. That, of course, is equal to the H plus times the C9H7O6 minus, and I apologize, my handwriting is terrible, over the C8 or C9. See, my handwriting is terrible. I can't even read it. 9H8O6. Okay. Since I know what this concentration is, because we again make the assumption that even though this is a minus x, that x is small, then I can plug that number directly in there. So I have 3.0 times 10 to the minus 4th is equal to x squared over 6.38 times 10 to the minus 5th. We then get that x squared is equal to 3.0 times 10 to the minus 4th times 6.38 times 10 to the minus fifth. That gives me 1.914 times 10 to the negative 8. That's what my calculator says. I then take the square root of both sides, get x alone. And that gives me 1.38 times 10 to the minus fourth to 3 sig figs because I started with 3 sig figs. So that's my value for x. I'm then going to take the pH is equal to the negative log of 1.38, and I'll rewrite it this time because I don't always. I usually just draw an arrow of that value. I take the negative log of that number on my calculator, and I end up with pH is equal to 3.859. Again, 3 decimal places because of the 3 sig figs in my starting numbers. Questions about that? Now, the only thing I will tell you here is that the more practice you do, the better. You will get to a point where you notice that I just almost go automatically from this is my setup to x squared over that initial number. That's because I've done this a million times. Okay. Did I have to start where I looked at everything and I said, okay, what was the concentration of this? What was the concentration of that? What are all these numbers that I'm doing here? Yes, absolutely. But doing this a million times gave me the ability to not have to do it as systematically. Okay. In my head, I can do those things. All right. I try not to do that in front of you guys just because you need to see the steps that I'm taking. All right. But the more practice you can get on these, the better. Because again, you're going to see these over and over and over again, especially on this first test and on the final. So being able to work with the ice tables, being able to manage them in whatever direction that we're doing them is going to become really important. Okay? Questions on that? So, want to take a short break before we talk about the bases? I've heard no indication of that, so we're not going to wait. Okay. So when we talk about our weak bases, any base that's not a strong base is a weak one. We talk about bases in a generic sense by listing them as B. So, and we always have that in the presence of H2O. We pick up a proton from the H2O and get an OH minus. Okay. Now, in some cases, we're just, doing this like RbOH directly gives Rb plus OH minus, but that's a strong base. So that's why we don't talk about it that way. We always talk about it in relationship or in relation to the reaction with water. My Kb is then defined as the concentration of the conjugate acid times the OH minus over that initial concentration of base. Okay. Now, the value of your pH is really related to the value of the K. Okay. Here, we're talking about the value of the pH being, and both the pH and the pOH are related to that value. Okay. So the bigger the Kb is, the larger the OH minus is going to be, and therefore your H plus is going to be smaller. So your pH is going to be higher. Okay. And in order for that to happen, the following conditions either must exist or help. Weak bonds between that metal, because it's almost always a metal, and the OH. Okay. That doesn't belong there. Gotta fix that. So weak bond between that metal, and it's almost always a metal that we're talking about, and that OH minus. The more stable that BH plus is, that's the better situation. And that MOH bond has to be polar. Hence, when we talk about the CaOH2, it's only slightly soluble because that bond is not that polar. And so it doesn't come apart that much. So it's not complete solubility on that particular species. Okay. So questions about that? So now we can look at a rice table for base equilibrium. Same kind of thing that we talked about before. Here we're going to talk about that is the wrong equation. So we're talking about NH3 reacting with H2O, give me NH4 plus, which is what's written in the table, plus OH minus. Okay, so that isn't what you see in this table right here. So NH3, NH4 plus, and that's a 4. It really is a 4 down here. And then the OH minus. Okay. Now I know that my KB for that is going to be the NH4 plus times the OH minus over the NH3. That also has a value of 1.8 times 10 to the minus 5th. Acetic acid and ammonia have the same K value. Right? My KB is going to be equal to X times X over the concentration of the NH3 because we make this assumption that this is small. Okay. So we set this up in exactly the same way that we did for our weak acids. Okay. We can substitute in our values. So KB is equal to 1.8 times 10 to the minus 5th. That's equal to the X times the X, so the NH4 plus times the OH minus, over the 0.5, the initial concentration of the NH3. We then solve for the X squared by doing 1.8 times 10 to the minus 5th times the 0.5. And that eventually, once I've taken the square root of both sides, gives me an X value of 0.0030. Okay. Now, if I do it in the quadratic sense, I can see that this is a very small number. Again, you do not have to worry about this part, but if you're curious about it, there it is. Okay. So this is really no different than what we did for our KAs. Handling KBs is really no different from that. Now, remember, if you get asked about a pH for this, you have to remember that the X that you solved for is equal to the concentration of the OH minus. And so if you take the negative log of the OH minus, which you can do, that gives me my POH, not the pH. There's one more step if you want that pH. You've got to do the pH is equal to 14 minus the POH. So you'll, and this is something that you'll see is when we ask about the bases, we often ask for pH as well to see if you remember that that is what you've solved for, is that OH minus, and therefore you need that other step in that equation to get to pH. Okay? So questions about that? So let's try a couple. Let's work with these. So methylamine is a base and has a KB of 4.4 times 10 to the minus 4th. What is the POH of a solution of methylamine that is 4.37 times 10 to the minus 2? Start with my equation. Always start with my equation. CH2, NH2. It's going to react with H2O. And I'm going to get a CH2, NH3 plus. So all I did was add an H plus to that. Okay. And that leaves me with the OH minus from the water. Okay, so that's my equation. Now, remember that this is aqueous, this is a liquid, this is aqueous, and this is aqueous. So that would give me a K equal to that CH2NH3 plus concentration times the OH minus concentration over the concentration of CH2NH2. Okay, so that's the K that I'm working with there. And again, I don't always list it, but this is a KB. So whether it's there or not is entirely up to you. I frankly don't care because I know what it is. So it's an equilibrium constant, therefore K is all you actually need. Okay. So if I have a balanced equation, that means I can put in some of my other stuff here. My initial condition on this base is 4.4 times 10 to the minus 4. That's from this question. So I've got that. I know that the value for this K is 4.3. No, I got that backwards. I apologize. I wrote that in the wrong place. That is not my initial condition. So that KB, I put in as the initial concentration. That's not right. 4.4 times 10 to the minus fourth goes there. The initial is that 4.37 times 10 to the minus 2. And this is when I say RTFQ, because I didn't read the question. So since I didn't read the full question, I didn't get things in the right place. So now I've dealt with that. And I'm looking for a POH, which is again, POH is the negative log of that OH minus that I'm going to solve for right there. Okay. I initially have none of either of those. We know technically that's not true, but again, the contribution from the water itself for the OH minus is extremely small, so we ignore that. When we do our change, we take one of these. That's a minus X. That's a minus X, but I don't care about that because that's a liquid, so I can draw through that. This is a plus X, and this is a plus X. And then when we have our final conditions, our equilibrium, 4.37 times 10 to the minus 2 minus X, we ignore the X. And then that gives me an X here and an X here. Okay, because that equilibrium row is always the sum of the rows above it. We then take our KB, which is again equal to the CH2NH3 plus times the OH minus over that CH2NH2. And then start plugging things in for that. That's going to be equal to X times X over 4.37 times 10 to the minus 2. Since I know that my KB is 4.4 times 10 to the minus 4th, I can multiply that times this number right here, the initial concentration of the acid or the base, 4.37 times 10 to the minus 2, and that's equal to X squared. So I can do happy math. Yay, happy math. 4.4 times 10 to the minus 4th times 4.37 times 10 to the minus 2. That gives me that X squared, and I've just flipped the equation around, is equal to 1.9228 times 10 to the minus 5th. I then take the square root of both sides. That gives me X is equal to 0.00438. And again, 3 sig figs, because I started with a number that had, no, actually I started with a number that had 2, well, okay. I'm gonna take that to 2 because the KB value that I'm working with only has 2 sig figs. So 0.0044 is the way that I report that. Now that's my OH minus concentration. So if I want a POH, that's the negative log of that number right there. So on my calculator, I hit negative log of that answer, and I end up with my POH equals 2.36, rounding because of 2 decimal places for the 2 sig figs that I had. Questions about that? I have one more KB that we can do if you guys want to walk through this again. If you're feeling comfortable, we can skip it. What do you guys think? If anyone wants to do it, I'll do it. I'm not hearing anything, so I'm going to skip it. I will put a solution up on D12 for this. And I will do a walkthrough on that as well. So questions about our weak bases? Well, let's talk about the relationship between Ka and Kb. So I've got a Ka, I've got a Kb, one's for an acid, one's for a base. Let's talk about the reaction of acetic acid to give the acetate ion. So I have my CH3COOH. It gives me H plus that CH3COO minus. That has a Ka of H plus times CH3COO minus over the CH3COOH. Okay? Now remember, acetate ion reacts with water. So we take our H2O, that acetate ion, CH3COO minus, that gives me back that acid, CH3COOH plus OH minus. And that has a Kb that can be associated with it. Okay. In that case, we're looking at the concentration of CH3COOH times the OH minus over CH3COO minus. Okay, awesome. That's fabulous. Related, not the same. Here's an interesting thing though. If I take this Ka and this Kb and I multiply them together, and that's all I've done right here is to write those two expressions there. Okay. I end up canceling this right here with that right there, and that right there with that right there. And that leaves me with H plus times OH minus, which is Kw. So if I multiply Ka times Kb, that gives me Kw. And that makes sense to me because all of this is happening in water solutions. Okay, so we need to take that Kw as part of all of this. It is part of all of this. It's not separate from it. And so that relationship makes sense. And what this means to you is that if you are given a Ka, but you need to know what the value of Kb is, you can solve for it using Ka times Kb equals Kw. Okay, so I know that if it's a good acid, it's not going to be a very good base. So if Ka is large, Kb will be small. If it's a good base, then it's not a very good acid. If Kb is large, Ka will be small. And I know that that's that inverse relationship because of this. That's how I know that. Okay, so we can find the other K if we're asked to do so. Sometimes we do this as an exercise to make sure that you understand the relationship between the two. Questions about that? Okay, so let's take a look at least one example of doing this. Acetic acid is a weak acid with a Ka of 1.8 times 10 to the minus 5th. What is the Kb of the conjugate base of acetic acid? And what's the formula of that conjugate base? Would sodium acetate be the acid or the conjugate base? So you'll see that all of these questions have basically the same structure. All right. So these are questions that are fairly typical for how we would look at this information. All right. So I have acetic acid, weak acid, Ka of 1.8 times 10 to the minus 5th. I want to know what Kb is. So I have Ka 1.8 times 10 to the minus 5th. I am working with acetic acid, which is CH3COOH. I want to know what is Kb. And the other thing, what is the formula of the conjugate base? Well, then I need to write the dissociation reaction for this. To give me that H plus the CH3COO minus, which is the conjugate base right there. That conjugate base has a name. It's an acetate ion. So if it says, would sodium acetate be the acid or the conjugate base, that is the salt of the conjugate base. Okay, so sodium acetate is the base. Okay. The other thing that it asked me for was Kb. So I know that Ka times Kb equals Kw. I'm pretty sure that this relationship is not in the formulas that you're given on the test. Again, this is one of those things where we just expect that by the time we get to the test, you've run through this enough times so that you could remember it. But if you don't remember it and you want it on the test, ask me and I'll tell you. Okay. I'm not going to fault you for that. So I know that Kw also has a value of 1 times 10 to the minus 14th at 25 degrees. And we'll make the assumption that we're at 25 degrees because I have no other value for Kw. I don't know anything else. I'd have to be told. So I'm going to assume that as well. So that means that my Kb is equal to 1 times 10 to the minus 14th, that Kw, divided by the Ka that I've been given, 1.8 times 10 to the minus 5th. And I can do happy math on that. If my calculator will let me. And I get my Kb value to be 5.55 times 10 to the minus 10th. And it actually should be 5.6 because I should have 2 sig figs. We assume that Kw is known infinitely, so we never consider it as our limiting factor in determining significant figures. Now, in the event that you're not at 25, that won't be the case. So questions about what I did or how I did it. Do you want to see another one of these? Or are you good with what we're doing here? Okay, I will again make an assumption that we are good. I will put answers and walk through on D2L for the other ones sometime after I get this posted. So another way that you might see this is given the K, find the other K. So if I give you a Ka, what's the Kb? Let's start with ascorbic acid. We'll do this one instead, the second one. I'm given a Ka of 8.0 times 10 to the minus 5th. I want to know what's the Kb. So Kb is equal to Kw divided by Ka. Kw is 1 times 10 to the minus 14th. Ka that I was given is 8.0 times 10 to the minus 5th. And that gives me the answer that I'm looking for. Now, are you expected to actually calculate that value and report the value? Yes. I need you to do the math. Okay. So even though I've seen this setup and that there are a large number of points that go with that setup, I need to see that you know how to do the math as well. So this is something that I've seen on some of the lab reports that I've been looking at. There'll be a setup, but not an actual calculation. And I need that calculation. On the flip side of that, I will tell you that if you give me a number without a calculation, that's going to be a problem too. And the reason that it's a problem is I need to know how you set it up, not because I need to check that you know how to set it up. I mean, although that is really important, that is. It's because if something went wrong between you setting it up and that number that you spit out, you should get credit for the setup that you did rather than getting no credit for the number that's wrong. Okay, so showing your work in doing this is incredibly important. 1.25 times 10 to the minus 10th is the value that I get there. Questions about that? And again, if there are no questions, I'm going to go ahead and move to the next one. Okay, now your textbook talks about 3 specific types of acids. I mention this only because it is important that we understand that these things exist. And sometimes you'll hear me throw these terms around, okay? So a hydrohalic acid is a hydrogen and a halogen. So HCl, HBr, HI, HF. Those are the 4 that we typically talk about. I mean, HAT is an acid, but it doesn't really work very well. HF is not a strong acid. The rest of them are. All right. The bond energy and the bond polarity are competing factors determining which is the strongest acid. So the enthalpy, the strength of the bond between the H and the halogen, predominates here. We'll talk about that enthalpy later on, all right? Because I know we haven't covered that yet. but that is something that we will come back to for the third test, and we'll talk about it again there. When we talk about oxoacids, we're talking about HO and something that's attached to. So an oxoacid would be something along that, well, and I don't want that one. Phenol is a great example, and that's a benzene ring. That has an OH on it. And so this is the R part, and then the O or the Z part, and the OH that we're talking about. So there's a Z here, and then the OH. Okay. And that benzene is highly electronegative. So that's an oxoacid. When we talk about carboxylic acids, we're talking about that COOH. That's what that means. And this actually looks like this. It's a Lewis structure. So this particular structure has a lot of stability in it. And depending on the nature of what's stuck to it, it could be a great acid or a terrible acid. It depends on what that is. Okay. What you'll see as as you move into organic, if you do, the nature of this bond determines everything. And so that's one of the things that we need to talk about, is the fact that these acids are affected by those Lewis structures in ways that we don't necessarily talk about. But that is why some things are good acids and some things are not. Okay? So questions about that? Awesome. You'll hear the term polyprotic acids. Now, poly means many, protic means H+, so that means anything that's got more than one acid on it that it can donate. Okay. So if we were to talk about an H2SO4, sulfuric is one of the ones that we talk about, which is a strong acid for its first proton donation. So we talk about H2SO4, and what it does is it becomes HSO4- plus H+, and that K is huge. Okay, but this can also act as an acid. That HSO4 can donate one proton to become SO4 2-. And when it does that, that is a weak acid. So it doesn't completely dissociate. And so remember I said, well, this is twice, except it's not. This is why. So one of those protons is completely dissociated. The other one is not. And so that complicates all the math. There are ways that we can calculate for polyprotic acids what the actual concentration will be, but we have to take into account all of those dissociations. That is not something you will be asked to do. Now, there are some slides in the original deck that I had where I walk through one of these, but they are not something you're going to have to do, so I'm not going to talk about them here. Okay, if you are curious about that, if you saw it and you want to talk about it, you and I can talk about it afterwards. That's perfectly fine. But that is not something you will be asked to do. So what are things that you might need to know about polyprotic acids? You need to know what the term means. So polyprotic means it has more than one acidic proton. That's what that means. And it will probably have multiple Ka values, which are not the same. So a couple of questions that I've asked in the past: which of these is a polyprotic acid? And only one of them, or a couple of them, if it's a choose all that are, have multiple protons on them that they can donate. Because of the way that these things look, the way that the many different ways that we can write them, if I am asking you that question, the acidic protons are always going to be written at the front. So it will only be the ones at the front of that formula that you'd be talking about. Okay. So notice, like oxalic acid, this guy, right? Where's my pen? Right there. He has two protons. One is here on the front end and one is here on the back end. I would never ask you about those, how many protons are on oxalic with it written that way. If I were going to ask it, I would write it as H2C2O4. And so then you'd see that there are two acidic protons. Okay? So just know that that's the way I handle that in terms of asking you on tests. Questions about polyprotics? Diprotic and polyprotic acids, again, more than one proton. Diprotic means it has two, polyprotic means many, can include two. So polyprotic applies to two as well. It has more than one acidic proton. This is typically done in successive steps, each with their own K value. And the K for the first step is always larger than the K for the second step. So we can do calculations for these the same way that we've done for other ones. Again, I will not ask you to do that. Okay? So questions about that part of it? Shouldn't be. It's mostly the same thing I just said. Hopefully I said it well. Now let's talk about another way that we can use Ka. Let's use the pH to calculate Ka. This sounds familiar. We're going to do this in the experiment that we're talking about. So the pH of a 0.1 molar solution of formic acid, HCOOH, at 25 degrees is 2.38. Calculate Ka for formic acid at this temperature. So my pH is 2.38. My H3O plus is then 10 to the negative pH. That's what this is, 10 to the negative pH. And that gives me this value right here. Okay. I can then take that value and put that into my ice table. So I've set up an ice table. I have my formic acid giving up that proton to give me that HCOO minus. Okay, my initial concentration is the 0.1 for the formic acid, and I assume 0 and 0 for those two. We have our change, negative X, and plus X, starting to look really familiar. And then we can solve for our equilibrium concentrations, because if I don't know all of those values at equilibrium, I can't calculate a K. I am making the assumption here that everything is really, really small. You can see that we've got a very similar number when we do this. So we could make that assumption. That's fine. That simplifies our math. And this is the value that I have for the X that we have here. So I know my Ka is equal to the H plus times the HCOO minus over that HCOOH. Okay, so I have my X as 4.169 times 10 to the minus third. That is going to be multiplied by itself, so I'm squaring that. And then I put that over the 0.1. Okay, now I will get some errors in doing that calculation that way, but that's fine. We can do it that way. Okay, so I take my 4.169 times 10 to the minus third, I square that, and then I divide that by 0.1, and that gives me 1.7. How many sig figs do I have? I have 2 decimal places on the pH, which means that this technically should be 4.2 if I were to report that, but I left it as this number because that's what my calculator spit out. So 4.2 times 10 to the minus third. That means that when I do all of this math, I should come out with 1.7 times 10 to the minus fourth. So 2 sig figs because I started with 2 decimal places. And that's my value of Ka. So this is another way that we see this. And this is what you're being asked to do in the lab, is to use that pH to calculate an H plus, which you then use to calculate K. So questions about that process? So I've just written down a couple of steps that I, this is what goes on in my head when I do this. So I thought it might be helpful for me to specify that. So when I calculate pH using Ka, I write the equilibrium equation for the ionization. I write the equilibrium constant expression. I set up my ice table for this and look at my X's, so function of change, substitute any equilibrium concentrations into the equilibrium constant expression and solve for X. And make assumptions if you can. Okay. In your case, we always do. So calculate the pH for 0.3 molar solution of acetic acid, HC2H3O2 at 25 degrees. I took the liberty of writing this equation this way, including the H2O liquid, Just as a reminder that that's what we're actually dealing with. If I do that, since this is a liquid, it doesn't appear in my table, which is why I haven't included it, and therefore why I write this like this. So I could have that H2O over here, but in my head, what happens is, okay, it doesn't look right, and that's why I don't ever include that part of it. That's why I don't put this as H3O plus, because in my head, that's not mass balanced, and it bothers me, right? So I have a 0.3 molar solution of the acetic acid, so 0.3 molar. I assume this is 0 and this is 0. I know that I have to take that apart to make my H plus and the anion from that. So my equilibrium's here, here, and 0.3 minus X. And I got rid of that. And I've dropped the M as I'm doing math. So cool. I could do that. Calculate the pH of acetic acid. What am I missing? In order for me to actually solve this, I need a value for Ka. So that is something that most people are like, well, okay, but I don't have that value. Well, actually, the acetic acid one, and I just want to verify that I remember it correctly, is on the exam handouts. And if I look at my exam handouts, where did my window go? I had this open. And I scroll forever until I get to some weak bases and weak acids. And I can scroll in on this. And I see acetic acid is right there. And it's 1.8 times 10 to the minus fifth, which is what I thought it was, but I wanted to verify that. So again, if you see this and you say, well, I'm missing stuff, you may be missing stuff because it's on the exam handout. Okay? So my Ka equals 1.8 times 10 to the minus fifth. So remember to use your resources. Okay, so 1.8 times 10 to the minus fifth is equal to 8x squared over 0.3. I know that x squared is equal to the 1.8 times 10 to the minus fifth times 0.3, 5.4 times 10 to the minus 6 is what my calculator spit out for that. Take the square root of both sides. And I get my x is equal to 0.0023 to 2 sig bigs, and that is molar. I know that that's equal to my H plus concentration from there. And so if I want a pH, that's the negative log of that number right there. And that gives me 2.63. Yeah, 2 decimal places because it's 2 sig figs. Now, you probably guessed that asking about a pH in this situation is going to be something that you're going to get asked to do in some way, shape, or form. Other things that can go around that, you may get asked for what's the pH, what's the POH, what's the H3O plus, what's the OH minus, all of which you should be able to find from knowing one of those values. Okay, so understand that there may be related questions to that using the fun box so that we can go through all of the math. Because we do this so many times, the expectation is that doing those calculations is not going to take you that much time. Okay. We can use pH to calculate Kb. Right? Similar to what we just did. We know that I have a 0.1 molar solution of ammonia. pH is 11.13. Calculate Kb for ammonia at this temperature. Now my Kb is equal to NH4 plus times OH minus over NH3. I'm given a pH. So I can't really use that as is to get this OH minus concentration, but I can take the KW and use that to work with this. Okay, so I can either take the 10 to the negative 11.13, which is the OH minus, and then divide that into KW, which was 1 times 10 to the minus 14th, which is what is written here. Or I can calculate that my POH is equal to 14 minus that 11.13 and do it that way. So if I do that, 14 minus 11.13, it gives me POH is equal to 2.87, and then 10 to the negative POH is my OH minus concentration. So that's another way that I can get to that number. It's entirely up to you which one you decide to do. Notice that that's what I did over here is at 2.7. My OH minus is a 10 to the negative 2.83, and that's equal to 0.0013. Now, if that's my OH minus, that's also equal to my NH4 plus. And so if I take my KB and I put 0.0013 squared over my 0.10, that should give me the KB for this. So take my 0.0013, I square that, I divide that by 0.1, and that gives me KB is equal to 1.69 times 10 to the minus 5th. Okay, so I've just done similar to what we did for the acid in terms of the KB, but we've got to remember that what we're given is pH, which doesn't directly relate to what we're looking at here. Okay, so questions about that? And again, the math that's in this table, this number right here, has everything to do with not making the assumption. This has to do with making. Just in case you're curious as to why these are not exactly the same. Okay? Questions about that? Okay. Do you want to do another example? I'm going to guess no. I can do a D2L walkthrough on this. For anybody who wants to see it. Any questions before we move on? Okay. So let's talk about buffers. We talked about them a little bit before we went into the lab. Now, a buffer is a weak, either weak acid in its conjugate base pair or weak base in its conjugate acid pair. Okay. These concentrations contain relatively high, they have to be relatively high concentrations, greater than 10 to the minus 3, for them to work as a buffer. Okay. And ideally, they'll be roughly equal in concentration so that we can add acid or base to it and get it to work. Okay. You may have seen, and you probably have seen, buffer solutions. Notice those colored solutions that we had in the lab that I was trying to use to calibrate the pH meters. Those are buffer solutions, and they're colored so that we know what pH they are. Okay. So our blue ones are our base, our red ones are our acid, and our yellow ones are the pH, and roughly neutral. So that's what we're looking at, and that's why they're the colors that they are, is because of what they look like on a pH spectrum. Okay, so that's what we use to calibrate them. Now, how a buffer works, if I have a buffered solution, it's made of HF and F minus, and they're equal concentrations. If I add H plus to that, so I add additional H to this, what happens is that the F minus that's present reacts with that H plus and gives me more HF. That means that my HF concentration has gone up, my F minus concentration has gone down because of that equilibrium. And that's what we see. But because I took up that H plus, it doesn't affect that concentration very much. Okay, so my pH doesn't really change because of that. On the opposite side, if I take this HF solution and I add an OH minus to it from, say, NaOH, then the HF reacts with the OH minus to give me H2O and F minus. And that means the concentration of HF has gone down and the F has gone up. So that's how our buffer works, is that we're changing that ratio between the two of them. That is not something that we typically see a change in pH for, all right? Now, there are two ways that we can make a buffer, and it's important that you know how this works. So I can take a weak acid and I can add its conjugate base to it. That's exactly what we did in the laboratory. We took the acetic acid, we added sodium acetate, because the acetate ion has to be stuck to something. So I put in sodium acetate because sodium doesn't react with anything. So therefore, that's a useful thing for me to do. I have to add the salt of that anion. So that's how I can do that. Okay. I could also use a weak base. I've seen them made with ammonia and an ammonium salt, which is my NH4. And common things we see here are NH4, NO3. Again, NO3s are always soluble, so therefore that's a good thing for us to work with. Okay, so that's one way. I can directly mix that weak thing with its conjugate and be done there. Here's the other thing though. If I take acetic acid, like we're going to do in experiment 3, and I titrate it, once I'm partway through that titration, then I'm in a buffer zone. And what you'll see in your pH curves when you're doing a titration is that you go up, you hit this flat, then you go up again. This is a buffer region. Okay, so you've created a buffer by reacting some of that acid to make its conjugate base. And when those concentrations are roughly equal to each other, then that gives you a buffer region. Okay, so that's another way that we can do this. So on the final, I know that there are questions about what are 2 ways that you can make a buffer. Those are your 2 ways. Okay. Now, it's not on all the finals, but it's on most of them. So questions about that? And one of the things that we talk about is the pH range and the buffer capacity. So the range of pH values over which a buffer system works effectively is near its optimal pH. And that's where the pH is equal to the pKa. If I have absolutely equal concentrations of the acid and its conjugate base, then that disappears from the Henderson-Hasselbalch equation. So remember, Henderson-Hasselbalch is pH equals pKa plus the log of the concentration of the A minus, the base, over the acid, HA. Okay, if these two are equal to each other, then we get the log of 1, and the log of 1 is 0. So pH equals pKa. So that's my optimal place for this. Now, if the concentration is more than 10 times the other, all right, then it becomes difficult to have real buffering range, all right? So the pH range of our buffer is usually plus or minus 1 pH unit from the pKa. Right? That's the way that we can talk about that. And pH will be the same for a conjugate acid-base pair, regardless of what that concentration is. But the buffer that's a higher concentration will be able to neutralize more before the pH changes, just because there's more of it around. So questions about that? So in practical solutions, they don't last forever. My buffer will eventually be exhausted and it can't continue to keep things from changing, right? Okay, so again, take my acid, add it to my buffer system. So here's my buffer containing HA and A minus. If I add a strong acid to that, that gives me this component here. I take that H plus from that strong acid, it reacts with the A minus to give me back that HA. I will then calculate the new values of HA and A minus. That has to be done in terms of moles. Once we've done that calculation and we have the moles, we divide by the total volume to get a molarity, and then we can use the Henderson-Hasselbalch equation to find our pH. Okay. We can go through the exact same process if we are adding strong base, okay, to see what the new concentrations of the HA and A minus are, and then using Ka, we can find pH. Okay, so that's how we can deal with that. So you may see that you have a buffer solution and you add some amount of like a 0.1 molar HCl to that. And just for the sake of argument, we could say we added 10 milliliters. And so the number of moles from that would be the 10 milliliters times the 0.1 molar. And then I have to have 1 liter is 1,000 milliliters. So the conversion of the milliliters to liters. Okay, some people can do that in their head. I can't. So that would tell me how many moles of the HCl that I've added. And then we can use that. If I know how many moles of HCl, that tells me how many moles of H plus I generated. And so I can do the math to see, okay, if my initial concentration of this was 0.4 molar, and I have some volume of that, let's say I started with 50 milliliters, 0.4 times 50 divided by 1,000, that tells me that initially my my anion and concentration of HA, because I'm assuming that they're the same initially, is 0.02 moles. And if I add to that, (0.001 moles of the H plus, then this 0.02 moles of HA. Sorry, I want to talk about the anion first. Minus the 0.001 moles of HCl, right? So 0.02 minus 0.001, that tells me the new concentration, 0.019 moles of the anion that are left, because they will have changed. That means that my HA will have gone up to 0.021 moles of H. And then we can calculate that concentration using my Henderson-Hasselbalch of base 0.019, but I haven't converted that. Oops. See, and this is why I was talking about it. So again, these are moles. So I need to make sure that I've divided by the total volume. If I added 10 milliliters here, I had 50 milliliters to start with, I would have to divide that by the 60 milliliters total to be able to put that into the Henderson-Hasselbalch equation. Remember that we have to deal with molarity in the Henderson-Hasselbalch. That was my point. Okay? So questions about that? That's my derivation of the Henderson-Hasselbalch equation. Again, your textbook goes through that in big detail if you really are curious about that. It's the pH, the POH, the H plus, and the OH minus of a buffer that is 0.12 molar in lactic acid, CH3, CHOH, COOH, and 0.10 molar in sodium lactate. Ka for lactic acid is 1.4 times 10 to the minus fourth. Finally, what's the concentration of CH3, CHOH, COOH in solution? Okay. So my pH is going to be equal to my pKa, which is the negative log of the Ka that I was given. That's what this is right here. Plus the log of the concentration of the base, the sodium lactate, so that's right there, over the acid, which was a 0.12 mole. Okay? That gives me 3.77 when I go through all the happy math. All right. Now, if I want the concentration of the H plus is equal to 10 to the negative pH. So I get 1.70 times 10 to the minus fourth. My POH is 14 minus the pH, which is 3.77, gives me 10.23. The OH minus is 10 to the negative POH. That gives me 5.98 times 10 to the minus 11th. And the concentration of CH3CHOH equals the initial concentration that I had minus that 0.170 times 10 to the minus 4th, which gives me this here. Okay. Questions about that? Now, do you guys have any of these that you'd like to go through in terms of sample questions? My purpose in putting this slide together was just to show you some of the questions that you might see on a test related to this material. Again, you have samples in the practice and on the practice exam of things that you can look at for these. Okay, so if you don't have any questions at this point, I will put up a D2L walkthrough on this. And that's everything we're going to talk about. So that's everything I had for today. Go. And I ended on time. Now, if you have questions about the lab 3 that you're doing today, the data that you got for that, or the experiment that was supposed to happen, any of that, or questions about experiment 2 that you want to talk about, then let's talk about that. And then when you guys are done talking to me, then we can close this out. If you come across another question after that and you want to talk to me again via WebEx, that is perfectly fine. Just send me an email and I will get back on and be happy to talk to you. And when I do that, I will respond with a slightly different WebEx link because this is a one-time link. So my normal office hours link will be the one that I use for that. Okay. So does anybody have any questions about the experiments? Okay. And if nobody has any questions, I will close this out. And again, if you want to talk to me about anything lab related, lecture related, anything like that, send me an email. I will be happy to get back on WebEx and talk to you guys about it. But I'm going to go ahead and close this out so that I can start the process of getting this uploaded for you guys and anybody else who might want to watch this again. Okay. Thanks, guys. Appreciate it.